Uh, Everybody's muted. So okay, I think we can start. If you're not speaking, please mute yourself. Okay, create extra noise. Okay, so it's a pleasure to have Renato Renner today, and Renato is a professor in the physics, right, department at ETH, and he done some really amazing work in quantum information and quantum cryptography, quantum thermodynamics, quantum communication. And today we're going to hear about optimal universal programming. Curious to hear what that is.
Okay, yes. Okay, thanks a lot for the introduction and for the invitation. Usually I would say it's a pleasure to be in Israel, but it's even still a pleasure to see some of you now. So I will start in a kind of rather general manner, and then it will become a little bit more technical, but please feel free to interrupt me at any point, even at the beginning. And it's about the general, maybe more kind of colloquial style things. So in the title, there is this universal process programming, and universal programming really refers to a computer science notion that was there long before quantum computing. So I usually draw boxes of stuff, and one box could be a universal computer. So what does a universal computer do? A universal computer is universal in the sense that it can execute any program, which means that it has as an input something that I call P, which is a description of the program, the algorithm, and then it also has data input. This is somehow the things we really want to work on. So I guess this distinction is very clear for everyone who uses computers or programs computer, that of course the program is something we can input to the computer, but at the end we also feed some data into it on which the algorithm runs. And then usually we also, of course, want to have an output, and I also call this D because I will already now use a formalism that is quite usual in quantum information, that we have registers, and if I have, for example, a circuit running on certain registers, then I don't relabel the registers while I'm running the circuit. So here is just the data. Here on the left-hand side is whatever goes in, and on the right-hand side is whatever comes out. And without loss of generality, I will assume that these keep the same dimension. So of course, I just choose the larger dimension of whatever I need. So this should be D-dimensional, which means in the classical world, I would just have D different states, or log D bits. Now in the classical realm, I would not normally draw this additional arrow on the right-hand side, but let me nevertheless do that. Of course, if I feed in the program, I could keep the register later where the program was fed in and just still also regard it as an output. This is kind of completely useless in a classical description, but we will see that in the quantum context, that's very useful. Now, actually, let me briefly switch slightly the mode of my screen.
I'm sorry. So why is the input the same as the output? Don't we want to compute something?
Yes. So, yeah, what I mean is only that the label of the register is the same. So it's not the state. So the way you should think of it is that at the input, I will have maybe some, once we look at quantum data, there will be some state, which I may call phi d. And at the output, I have something like phi prime d. So the label of the register is the same. So it's the same physical register that carries it. That's what I call d. But the state of it, which encodes the information, is a different one. So you should just think of it, I have some, let's say, 50 qubits in a computer, and at the beginning, before I run my calculation, I initialize them to a state phi, and at the end of the calculation, it's phi prime, but they're the same qubits, the same physical things.
I can think of this as a Turing machine?
You can, yes. Yes, that's a possibility. You could think of the D as the tape of the Turing machine, for example. And of course, you would then maybe have another tape with the program on it. And there are just two tapes, a program tape and a data tape. Does this help? Okay. So now in the classical realm, I mean, all computers we have currently are, or most computers are probably universal computers in that sense, that we can just put in any desired program and in principle do any computation. Of course, not everything is computable, but if we are looking at finite size machines, so if I fix this dimension here, which I did, I just said it's a d-dimensional thing, then in principle, anything that can be computed from this input data could be computed by a universal computer. Now, I'm interested in quantum computation, and in quantum computation, the most general thing we can do is to say that an algorithm, however complicated it is, will calculate the output depending on the input, and the dependence will be given by some unitary. So in quantum computation, we will have the following relation, that phi prime d, that's the output data, is some unitary of phi d. So you could think of the unitary as something that is just a composition of many elementary unitaries. So for example, you have the individual gates, a control NOT or a NOT gate or whatever, and you compose all of them. Each of them is unitary, and then of course the total thing is still unitary. So that's just a very general statement saying that whatever model you have, even if it's a quantum Turing machine or a circuit model, you will always be able to say, to write it down in that way.
Renato, sorry,
Yes.
Can I ask a question?
Yes, of course, yes.
So doesn't it need to be unitary on the entire space? Namely, if the program is used as the control, then on the data it might be non-unitary because it is unitary on the total data and program.
Yes, you're perfectly right. That's also something I will require just a bit later. So for the moment, what I say here is actually in a way a restriction. You see in the title I have of unitary gates. So this unitary in the title refers to this U. So this is what I want to do with the computer. I'm somehow interested to program something which acts unitarily on D. Now it is true, as you correctly point out, that the whole machine, if I now write down, let's say, how does this machine act on everything? So this goes, I'm now going a bit ahead, but of course what I'm going to do is to say this P in a quantum world, the program could also be something quantum mechanical. Usually we think of a program as a classical description of something I can write on a piece of paper. But there is no reason to do so. I could also say a program could in principle itself be something that is encoded into quantum bits, into the state of a quantum system. And then this entire thing, which I may call C, or I will anyway call it like that. So C is, let's say, the total operation of the universal computer will again be unitary. So there will be something like a C that acts on P. So it takes the program, it takes D, and again outputs P and D, and this should be unitary anyway. So what I now said so far is essentially only that the U, which is only the thing that acts on D, should be unitary. Now there's a distinction between these two. This is somehow what I want to implement by my program, and this is just given essentially by physics. The whole operation will be unitary because physics is unitary. So how does this answer your question?
Sorry, I was muted. So it's
okay, right, yes.
Okay.
Okay, so it will probably even become clearer later, but let's for the moment go back to the kind of half classical case. By half classical, I mean the way we think currently of quantum computers. So actually, we, here in Zurich, the students who do we have here lots of students who now do master projects with companies like IBM, and there they really design quantum programs. But these students still work classical in the sense that they write down a program that in their master thesis, I probably couldn't read a master thesis that wasn't classical, and it usually contains algorithms. So this input here is a classical thing. And we can now ask, or generally what we tell these students in a way is we give them a unitary. We say, this is an interesting problem. This problem, if you write it down, explicitly corresponds to that unitary. Of course, I mean, anything is a unitary, even classical thing. Like if I say, talk about the factoring problem, that's at the end a unitary that needs to be carried out on the quantum computer. So very roughly speaking, a master project nowadays consists of me specifying a unitary and the student finding a program that implements it on the quantum computer. That's of course a very simplified view, but just to illustrate that. Now you can ask, if I specify the unitary, how large does the program at least need to be in general to implement that unitary, to implement the desired operation on the quantum computer? And of course, normal problems we have, like factoring, have a lot of structure, and therefore the programs are kind of much shorter than they would need to be compared to a case where I would just be malicious and sample an arbitrary unitary using some random number generator. I just write down an arbitrary matrix, and you could imagine I now, let's say, run out of ideas for master projects. I go there and just use a random number generator, write down the entries of a matrix. It would actually be, I still would have to think a bit to make sure it's at the end unitary, but I would create all these random numbers. So I still want to be sure it's unitary. So I have this boundary condition, and I give this matrix to the student and ask him, please program that. Then he would probably not find a program that is shorter than just one that specifies each of these entries, because there's just that much information. If I change something a little bit, the program would change. So I could ask myself, how many bits do I need to essentially provide at the end to this machine so that it can execute this unitary? And now the trivial answer would be, I just count how many bits I need to specify this unitary. So how many bits do I need to specify a unitary? I could, maybe in terms of bits, it's a bit hard to do, but I could just count how many real numbers I need. Of course, what I mean is a real number up to a certain precision usually, but what is the number of real numbers needed to specify this matrix? Of course, the matrix just has 2D or has D squared entries, but each entry is a complex number. So I need 2D squared real numbers, but there is this boundary condition that I wrote down, and this boundary condition is a boundary condition. It's actually a set of equations. These are themselves D squared equations, because that's itself a Hermitian matrix, and the Hermitian matrix has essentially D squared entries, so I can just subtract D squared. And if I really want to be precise, I can even subtract 1, because I probably wouldn't make a distinction between unitaries that are just different by a phase. So I lose one more degree of freedom. But this is the number of, this is how many real numbers I would need to provide to you to specify a unitary. And so we would expect that the number of bits that I need to input into a computer in the most general case, when the unitaries have no structure, is essentially this times the number of bits I need to specify a real number. So roughly speaking, the cost, I call this the cost in the following. So the cost is how long is the program? Let me maybe define it for a moment. So the cost would be the number of bits, or later when we talk about quantum program, about qubits required for P. So how large is this stuff here that I input? And the calculation that I just made is, of course, I could do this in this trivial way I just mentioned. And the trivial way is really to just specify each of these U. So somehow, if I do that, I get D squared minus 1 real numbers, and each real number I need to specify up to a certain precision epsilon. And to specify a real number up to a precision of epsilon, I need essentially of the order of log 1 over epsilon bits up to a constant, which depends on what distance measure I use and stuff like that. Okay. Now, that's just a setup. So we are interested in universal computation. And if we are interested in universal computation, an important point is how long do the programs need to be? And the main question I would like to ask is whether a computation or whether such a universal computer would profit from giving the input here really as quantum bits. Because that was now a completely classical procedure. I just counted how many real numbers I need to specify. And of course, once I have these real numbers, that's a classical description. That's just something I could input directly into this universal machine. To answer this question, I first probably should make this question a little bit more precise. So now this was kind of an introduction, but let me just draw this box again, but now add a few things to the picture. So first of all, we have this operation that acts on the whole thing. So it's again, as before, we have the program input and we have the data input and potentially again, the program that comes out and the data, the output of the computation. And what I would really like is to somehow say that on the data, I have a unitary. So I could draw a blue box here around this. And the blue box includes now the program. So let me make this a bit smaller. So here is the program input. And to execute a certain program, I could say in the most general case, when I can feed into this computer a quantum input, I encode the program into a quantum state, psi p. So in other words, if I now go back to this scenario, I specify a unitary and want the student to program the quantum computer with this unitary. Now, the question is, could there exist a very good universal quantum computer with the feature that it takes as a program, not classical programs, but potentially some quantum programs, or something encoded in a quantum state, which is potentially much shorter, which doesn't need to be that long, such that it still carries out the correct unitary. So of course, this input will depend on the unitary. But you see, when I now look at only the blue part, so if you consider only the blue thing, then this is something that only takes D as an input and outputs D. And I call this blue part G. And what I want, so the desired property, maybe that's the desideratum, so to speak, is that the G that I get, so this blue box, is really essentially the U. So if I only look at how the box acts on D, then it carries out the U, provided that I gave in the encoding of the program that encodes U. So that's the second.
Renato, I have a question.
Yes.
So if I understand correctly, the cost you defined doesn't imply anything about the circuit, the depth of the circuit.
Yes, right. Yes, so thanks for this question. That's a very good question. So here I'm actually I'm actually looking at things from an information theoretic viewpoint. So not from a complexity viewpoint. So in principle, so there could be a program that is very short in terms of the description here, in terms of the encoding, but in terms of complexity, it's very long. I mean, I could, in a way, describe a very long circuit, one that has exponential runtime in very short words, and like an exponential search algorithm, for example. It's an extremely long runtime, but the description is long. So here we are really talking about the description of the algorithm, not about the running time it has on the computer, which is a very different question. So I should have pointed this out. So it's really an excellent question. And of course, in practice, we are, of course, also interested in the time it takes to compute this. But now we just ignore the time. Not because I'm not interested in it, simply because it's much, much harder to make any general statements about time. So we're already happy if we can know how long is the description of the program potentially. But it's in a way a quite different question. Now, formally speaking, if I call this thing here C, what is G? I just write it down. So the G is an operation that, as I said, goes from D to D, and it depends on U, and it kind of acts on D. So it takes one input, which I indicate by a dot. But what it is it's essentially the operation C, which would go from DP to DP, where I leave the data register open. So the dot just means I don't fill it in with anything, but input into the program the state that encodes the program for the unitary U. So that's just in formulas written what I've here sketched. Just means that's what we mean by the execution of the universal. So this universal processor is executed, and it realizes what it realizes on the data is what I call G. And now I can also make the requirement a bit more, let's say, fine-grained. Before I just said that it should be equal to U, and now call it desideratum epsilon, is a slightly weaker version of that. I could maybe already be happy if this whole processor doesn't exactly implement U, but it may just implement something which is very close to U. So the distance between what the G does and what U does may be still positive, but as long as it's small, I may also be happy enough with that. So that's essentially what we may want. So we want that there is a program. Okay, maybe to summarize what we would like to have, if I go back to this picture, is we want to ask ourselves, is there such a box which takes an as short as possible program, which may be encoded in a quantum state, such that for any desired unitary, so this should be true for all U, I should write this here, for all U, for all unitaries, what this box does, it executes on this data here that is fed in the unitary to a precision epsilon in this sense. This little diamond here indicates the distance measure. So for those who are familiar with it, it's a diamond norm. It's essentially defined by taking any state that is also entangled with a reference, inputting it into this and inputting into that, and then calculate the trace distance between the outputs of the state and the reference together, and optimize over all possible inputs or maximize over all possible inputs. But it's just a distance measure, which has actually an operational meaning, which is probably more important, namely that the probability that at the end the result, if you have a classical result of the computation, would be different in the two cases. In the case of the real unitary U that you want to execute, and in the case of the actual G that you execute, if this difference is small, then also this is smaller than epsilon, then also the probability that you make an error is smaller than epsilon.
I have a question, Renato.
Yes.
Do you allow the output data bits and the output program bits to be entangled or not?
Whether I allow that? Yeah, that's an extremely good question. The answer we will see is that it's necessary to require that they are not entangled. But we will come back to that. But that's really an excellent question, because it actually goes a lot into the ideas of a proof of a theorem, which is the next one I want to demonstrate, which is a very old theorem. So now I will actually spend some time talking about an old result. And by old, I mean a really very old one for quantum computing, let's say, time scales. And that means something of the last millennium. That's already old. Namely, it's by Nielsen and Schwang. And I think this was a PRL paper. This is not the book of Nielsen and Schwang. They also had some research papers from 1997. So I think they developed that even before I knew any quantum mechanics myself. That's why, at least for me, it's old. And the theorem is very simple. It says for epsilon equal to 0, no, okay, now write it in words, but I've given the formulas above. No universal processor exists. So it's even independently of the cost. So in other words, what they say is you can never make this distance equal to 0 for all unitaries. Now you may think this is kind of maybe almost obvious for the following reason. So let's look at this. I told you that a unitary is this continuous object. It consists of d squared minus 1 different real numbers. And of course, if I want to make something exactly corresponding to a real number, I need infinitely many bits to specify it. And if I need infinitely many bits of this, this cannot exist. So maybe I should add that what they assume when they say doesn't exist. They assume that only things with finite size inputs can exist, because we are talking here about devices. And of course, we don't have a computer with infinitely many inputs. So the claim is more precisely that epsilon equals 0 cannot be achieved with any finite program size. And so you would say, okay, of course, you cannot express a unitary, which is a continuous object, with a finite program. So clearly, this theorem must be true. But why is it, okay, it's actually not that simple, because there's another thought or line of thought that would make you think that it's actually true. And the other line of thought is the following. I remember that I allowed the program to be a quantum state. And now we could get to the idea to say that there is something you may have learned in quantum information classes, which is called the Choya-Minkowski representation of a channel or of a unitary. So what you can do is you define a state. You could define the state psi p u as the state you obtain by taking the unitary you want to implement on your computer, tensor it with the identity, and apply it to some state theta, which I define to be an entangled state between d and some copy of d, which I call d bar. So if you have heard of Choya-Minkowski, you should be familiar with that. So the idea is really you can somehow encode all information that is in a unitary in a quantum state. The way you do it, you prepare a quantum state on two systems that are of equal size. Each system has the size of the system on which the unitary acts. So for example, if the unitary just acts on 1 qubit, then take a state, an entangled state between 2 qubits, act with the unitary on one of them, and do nothing with the other one. And then you get an entangled state still of the 2 qubits. And the claim is now that if I give you the description of this state, then you know everything about the unitary. So this simple 2 qubit state encodes all information that you need in order to reconstruct the unitary. So that would suggest that indeed information theoretically, if I just look at what I gave in here, if I would input that state, this processor in principle has all information needed to execute the unitary. That's why you would think, okay, maybe it's still possible to do it. Now, of course, it's not obvious, because when I told you all information you need to reconstruct U is in this unitary, is in this state. Sorry, I said all information to reconstruct U is in this state. Of course, this processor doesn't have a description of the state. It only has the state itself. There's, of course, a difference between me having on a piece of paper a description of an entangled state, where I can really look at all the amplitudes, and just having 2 qubits with that state prepared in that state. The first thing is much more informative because I really see all aspects, whereas if I just have the 2 qubits, I somehow need to read out what's inside. And of course, I cannot measure it, or of course, I can measure it, but if I measure it, I don't get all information that was encoded in the state. So you see, there are these 2 thoughts one can have. On one hand, I could say, trivially, it cannot exist. On the other hand, I could say, maybe there's a way, because in principle, everything can be encoded into that state. But the theorem now tells us, no, the answer is it cannot. You cannot do that. But maybe another example, just to illustrate that it's not obvious that this is the right answer, is quantum teleportation. There you somehow take a state and move it to another place by just sending 2 qubits, but the state is transferred perfectly. So you could also say this should be impossible because the state has real parameters by which it is characterized. So how can it be that all these real parameters to infinite precision are transferred in teleportation? But there we know it works. Okay, this is all to say that this theorem is not completely obvious. Nevertheless, it's of course true, and I would like to give you proof. So this is now kind of historic part of the lecture. This is not a proof I found, but I decided to just show you that proof because the proof we have is in some way a generalization of the ideas there. And I think it's useful to know that proof, even though I will probably not have much time to show you my proof. I think it's more useful for you to know the proof of Nielsen and Schwang at this point, because then you can probably imagine how our proof works. I will then make a few remarks. So let me just go through their proof, which is, I think, a very nice piece of information of quantum information theory that is anyway worth knowing. So let U and B be 2 different unitaries. So that's just the way we want to analyze that. We say that let's see how this quantum processor acts when we have 2 different unitaries and compare their action. Now, as I said before, the whole processor can be treated as a unitary itself. If it's not unitary, if this universal quantum computer that you see on the right-hand side wouldn't act like unitary, you could still look at its so-called Stein spring dilation. So that's just a technical term to say that if you include everything and don't neglect any degrees of freedom, then it certainly is unitary. So we assume that this whole C operation that I wrote down before, which acts on the data and on the program, is a unitary operation. And now it will actually be useful if I call here the output P bar, just to keep track of that, and what is the input and what is the output. For the data, we don't require that. So this thing, of course, takes the data.
Why don't you also require that? I mean, why do you use a special notation for the output of the program and not the data?
Okay, I could also, yeah, let me also do it for the data. I mean, there was no reason except for just I don't need it later in the proof.
Oh, okay.
Let me also do it for the data. It's maybe more consistent to explain it like that. So what I give to the processor is, of course, the state of the data on which I want to do a computation and the encoding of the program. So here, I should remark, here I really want to have a product state because this is just a program and I don't want the program to already know the data on which I act. So just referring to Josi's question before, he asked, of course, about the output, but at the input, I start with a product state. That's natural. It's just saying, it's essentially the idea that a program is I should be able to program a computer before I have the concrete data. And now what comes out, and this will now answer the question from before, I get a new state on side P. Here I get something on D bar in this notation. And if you now ask yourself, could this also be an entangled state? The answer is no, for the following reason. Of course, on the data output, so on D bar, if I now call it like that, I really want to have U of phi D. That's what it means that the processor works correctly. I really want that here it's as if I applied the correct unitary on phi d. Now there is a kind of little statement, which is very easy to see from quantum information, that says that if I have an arbitrary bipartite state, but I know that on one subsystem, I just have already a pure state, which is the case. So this, I assume that okay, for this proof, I just act on input data that is in a pure state. Then, of course, U of phi d is again a pure state. And now the point is that if I have on one register a pure state, then it can not be that the state is entangled. So it has to act as product form. So as a maybe just a proof idea is to say for an arbitrary state, I can always do a Schmidt decomposition. And if the Schmidt decomposition has more than one component, so if it's not of this form, then necessarily on both subsystems, I have not a pure state, I have a strictly mixed state. So that's how.
Do you mean when you trace over? Do you mean when you would trace over the program? You have a mixed state over
yes,
over the
yes.
data.
So maybe just as a little remark. So the statement is if I have something like psi for two arbitrary systems or rho AB, and if I know this state is such that rho A is pure, then I can always say that rho AB as a total state has product form. That's the statement I'm using. So that was kind of used here to write it down. And I hope this answers Josi's question, which, as I said, was kind of in that sense an important question because it appears here very explicitly. Now, I just copy the whole thing again with V, because as I said, we want to apply to two different unitaries. So I could also write down the whole thing with V. And of course, the output here, I don't require anything about the output on the program register, except that it's still some state that may depend on U and on V. So I'm not necessarily requiring that this is still the same as the input program. That's why I also put the bar here. So the program may be destroyed by the universal computer. I wouldn't mind, in a way.
Just to make sure, Renato, so C is a unitary, necessarily a unitary operation, or you're allowing it to be?
Yes, so C is the operation and that describes the action of the whole computer. And now I assume that the total computer, that was Tal's remark, I think, that the whole computer should also be unitary. And of course, a computer may not be unitary, that's an assumption, but I could always look at a unitary extension of the computer and do the proof with that, and nothing would change because I'm not interested in this output here. So I can just any extension including to P bar. That was actually the technical reason why I called it P bar, because it may include additional stuff that is not included in P.
But you could allow, like, for measurements on, say, on the program part at the end, and then it would not be unitary.
Yes.
That would not somehow.
That's correct. But then I would exactly use this time spring dilation idea and say, if there was a measurement, I model that as a control, not with an additional ancillary register, and then the total thing is again unitary.
Thank you. Thank you.
Okay. So far, we haven't progressed far in the proof. I just wrote down essentially that if I apply this whole process to the input, I get an output which is still product form. But now the crucial point in the proof is that what we can do next is compare the scalar product between the left-hand sides of these equations and the right-hand sides. And of course, they need to be the same, but they also need the same if I drop this C, because C is a unitary, and of course, a unitary doesn't change the scalar product. So if I drop this and this, then the scalar product between only this input and this input should still be the same as the scalar product between this and this. That's the idea. I hope that's clear, but it's really just, I'm saying this thing here doesn't have an influence on the scalar product because it's a unitary. The unitary is by definition something that doesn't change the scalar product. So let me write it down, and then if it's unclear, you may still, of course, ask questions. So I just take the scalar product of the input to C between the two possible inputs corresponding to the two possible unitaries. So that's this. That's the scalar product between the left-hand side and the scalar product between the right-hand side. So see it here on my slide here, or a slide on my notes here. And the scalar product here is of the form U phi d tensor psi bar p bar of U, and then the same with V. So that's essentially what we have if we that was a psi. So I just copy these two states on the right-hand side and put them into the scalar product. That's all. Okay. Now I have an equality, and now I transform this equality a bit. So, I mean, this will not be more technical than now. So if you could follow until now, I think we can just proceed to the end. The only thing I need now is that if I take a scalar product between tensor products, this is just the product of the scalar products. So in other words, the left-hand side of the equality can be written by a scalar product of phi d, and then times the scalar product between psi pu and psi pv.
Are you not missing the u's and the v's there? Ah, okay, right.
Yes, so I was first taking this term with that.
I see, yeah. Mm-hmm.
And now times this term scalar product with this. And this whole thing should still be equal to the stuff below. And below I again use the same trick. I mean, I just write this as a product between the two scalar products. So I get phi d, and here I, in addition, take the u on the other side. So, you know, in a scalar product, I can always shift one unitary to the other side by taking that joint. So that's this. And then the second term is just this psi p bar that depends on u, and the psi p bar that depends on v. So now I've just written it in a slightly nicer form. And this is, of course, useful because this term here is just equal to 1. That's just the scalar product of a state with itself. And okay, now we have the simpler equation that this thing is equal to this product. Now, let me mark this whole equation by a star because we will refer to it later. Now, I look at this term. This term here, I want to prove that this green underlined term is actually 0. But I'm doing that by assuming that it's not, so by contradiction. So suppose that by contradiction, so that's really the nicest way to see it, that this green thing, which I just indicate in my box, is not equal to 0. And then we'll see that that cannot be. So if it's not equal to 0, then what I can, of course, divide both sides by this term. I'll just now, yes. No, I think there's still enough space here. It's psi v p, and now I divide it by the green stuff. So I have here psi bar, p bar, that depends on u, and psi bar, p bar, that depends on v, like this. And on the right-hand side, what is left is just phi d u adjoint v and phi d again. Now the important observation comes here. The left-hand side has no phi d in it, which means that the right-hand side can also not depend on phi d. So let me underline this. So this orange thing must be independent of phi d. But this is very useful because if I know that this, I mean, it's just independent of phi d because the left-hand side is independent of phi d. But if I know that for any phi d, this has to have the same value, this can only be if this thing in the middle is the identity, or maybe some multiple of the identity. So it follows from that u dagger d must, u dagger v must essentially be the identity up to some, let's say, factor gamma. And this is the only way you can if you sandwich some matrix with the state and say the result should be independent of the state, then that's the matrix can only be the identity. That's the claim here. That's also easy to see. I mean, you can, for example, think of actually going into a diagonal basis, and then, of course, this means that all eigenvalues are the same. And if all are the same, then it's necessarily proportional to the identity. Okay, now we are almost done, because if this is the identity, then we could also write that therefore V, the matrix V, is just gamma times U. That just follows from the above. But this is a contradiction because, okay, maybe yes, here I assume that U and V are two different unitaries. I should have added that by different, I mean different by more than just the global phase. Because if they're the same up to a global phase, then they're the same computation. So by different, really, I mean that exactly that this doesn't hold. There's no way to write one as a scalar times the other. So therefore we have this contradiction to what I assumed here. So remember, I assumed that this green term is not equal to 0. Now we know it's 0. So we know the green stuff. Let me just write this. So we know this green thing is therefore equal to 0. And now we're almost done. Because of course, if the green thing is equal to 0, then the whole right-hand side is equal to 0. This here is 1, so it's irrelevant. But then this thing must be 0. So the scalar product between the two input programs must be 0. So let me just write this. So we found psi p u psi p v is equal to 0. Now, why is this sufficient? So what we have shown now is that for two arbitrary different unitaries, if we take the scalar product of the encodings, so remember, we encode these unitaries and put them into the program. For any two different unitaries, the programs, so to speak, the states that encode their programs have to be orthogonal to each other. But there are infinitely many unitaries you could think of. That they all have to be orthogonal. So we would need infinitely many possible orthogonal states. And that means there cannot be a finite size machine taking this input. So the result is that P must be, maybe it's, the first thing is that the support, so to speak. So if I look at all possible encodings for all U, and that's just a mathematical way to write that, is infinitely large. And that means P, the input register, would be infinitely large. Okay, so that was this historic proof. That's the so-called no programming theorem. It just tells us there is no way to encode a unitary into a quantum state such that a universal processor could somehow then execute this unitary. Now this seems to be, I mean, obviously this is kind of a negative result, but the point of our result, and I will only state it. So the idea was that the technical part of my talk is essentially this historic proof. And now I'll just state the result as essentially now something that again gives it a more positive spin. Because you could now ask, okay, let's accept the fact that we cannot implement an arbitrary unitary, but let's now go to this desideratum epsilon and just say, let's tolerate an error epsilon. What is then, is it then possible? And if yes, how large does the program need to be? And this is the result that I recently got with the two authors that were mentioned at the beginning, Yushang Yang and Giulio Chiribella. And the result is the following. So I'll just explain it, but let me first write it down. So the cost, again, is the number of qubits of the program. And we have a lower and an upper bound, and the two somehow match in the asymptotic regime where epsilon is small. So you should really think of the result as telling you something for a relatively small epsilon, small compared to the dimension d. So think of d, I mean, d could be relatively small. Let's say you just are even interested in implementing 3 qubits. You want to have a machine that implements any 3 qubit gate. So d would just be 8 or something. But you want to achieve a very high precision, so epsilon should be small. So what is in the logarithm is actually not so important. The important thing is at the end, the scaling. And here I just wrote an alpha for any alpha smaller than d squared minus 1 over 2. So what this result tells you essentially is that you see on the left-hand side, I have something that scales almost with d squared minus 1 over 2. A little bit smaller, so it has to be slightly smaller. Of course, depending on how much smaller it is, you have a different constant here. On the right-hand side, you have d squared minus 1 over 2. So roughly speaking, and in particular in the regime, so if epsilon is sufficiently small, so somehow much smaller than 1 over d4 to the 4, I'm writing that because then in this term, the epsilon, the 1 over epsilon dominates. We have one could summarize this by saying the cost is approximately given by d squared minus 1 over 2 log 1 over epsilon up to constant terms. So in other words, the size of the program really scales in the same way almost as in this classical trivial example I gave you. So at the beginning, remember I said one way to implement this is to just giving a classical description of the unitary. And then I said, if it's a classical description, the number of real numbers I would need to provide is this thing. This is d squared minus 1. Real numbers. So here we just have essentially improvement by a factor of 2, which of course is, depends also on what we have here in the logarithm. So in other words, our result is on the one hand a negative one. It tells us a quantum state doesn't really help much. It just at most gives you this factor of 2, like in dense coding or so. We also have a factor of 2. On the other hand, because it matches upper bound, we now know almost precisely what the cost is. So we now almost perfectly understand how well could such a universal processor work. So the answer is providing a quantum state. So the idea of encoding the input into a quantum state gives you an advantage essentially of 1/2. So you need only half as many qubits as you would need when you would just use a kind of conventional classical quantum computer, meaning one that takes a classical program as input. Maybe let me repeat that this is all just in this information theoretic way. So it doesn't mean a quantum computer has no advantage in terms of computation time, but essentially it tells you that in terms of the size of a description of a program, that I need a fully quantum computer, one that even takes the program as quantum input, has no advantage towards, in a way, a conventional quantum computer, one that takes the program in a classical manner. So that's essentially what the result tells us. Now, I think the time is almost over. I didn't say anything about the proof, but the idea of the proof is, in a way, the following. So let me just give the idea of it. So,
Renato, just to make sure, the task that you gave this cost function for is the one, I mean, the one with the diamond norm. So right?
Yes,
so
that's right. Yes, yes, right. That's why I gave this precise definition, because indeed there would be additional factors if you, for example, look at certain fidelities or so.
Right.
Of course, the overall result up to factors wouldn't really change, but factors would be different.
Yeah.
But we would still essentially conclude that there is no big advantage. I mean, let's say it would be, of course, much nicer if, for example, there was no square dependence on D or something like that. But now we know it's just a fact. It's not that we can still hope for an improvement, because the gap between the lower and upper bound is essentially disappearing in the small epsilon regime.
Thank you.
Okay, but I'm not, let me, maybe before talking about the proof, let me just give you a conjecture, because that's maybe more interesting for those who work on these things. So, and it also connects it a bit more to actual computation, because here I was in this artificial setting in a way where I said, let's just specify an arbitrary unitary. And of course, we are generally not interested in any unitary, but there are only maybe some unitaries which are really interesting to execute on a computer. It's maybe hard to specify this set, but let's suppose we have that set somehow characterized. So suppose that the set of, let's call it interesting, not just random, unitaries, U, and let's suppose that this can also be parameterized by some real parameters. And let's suppose there are many real parameters. And now this is only conjecture, but of course it agrees with our result in the special case where the set of all unitaries is considered. And also we looked at some other, let's say, we have some other evidence, but it's not a proof, that the same result would essentially hold. So in the case of the unitaries, remember we had d squared minus 1 parameters, and the cost was d squared minus 1 divided by 2. And now, and from the proof and so on, it seems like this should be more generally true. Namely that whenever you have something characterized by new parameters, you have new half as a scaling factor here. But that's something that we neither have a lower nor an upper bound for, really. So that's completely open in the general case. Let me maybe, yes.
Sorry. You go. I'll ask at the end. Sorry.
Yeah, let me maybe just spend 1 minute on the proof idea. And if you look at this process for the proof, it's actually important that we have this P here. The proof idea is to do for the lower bound the following. We kind of create a contradiction, so to speak. So we turn everything into a coding problem. So let's suppose someone has a unitary U and wants to encode it into a quantum state psi p U. I mean, that's what we would do in our setup. And then he feeds it into this machine that we had before. So this is the program, and the machine takes data. But let's suppose now, after executing the machine, there would be some little operation, let me put it in orange, kind of recovery operation that would recover the state psi pu. And now we could feed it again into the universal processor because we have recovered the program. So we could again do it, and we could do that, repeat that many times. We could again recover it and so on. Now, if we do that many times, we could collect the output of the computation for different inputs. So there would be an input phi 1, phi 2. So what we have here is actually U applied to phi 1, U applied to phi 2, and we could, as often as we repeat it, we would have all these inputs. And we have, if we have the same unitary applied to different states, we could, of course, by clever measurements, reconstruct the unitary, or at least a good guess for the unitary. Now, the proof works as follows. If the epsilon distance between the real state that is generated and this desired state u phi is very small, one can show that then we can also recover the program. So in a way, the better the universal processor executes the unitary, the less disturbed is the program itself. That's kind of clear because actually, again, of this fact that we saw that the output is really in the perfect case is a product state. That's what we had here. And so product state means that the program is not polluted by the data, so to speak. So we can reconstruct the program and execute it many times. So here is again the program, and then it's run again. And so if you have many executions of this, we have many data points, we have many times applied the U to a state phi, so we can recover the U very well. And if you can recover it very well, then there's a lot of mutual information between U and this recovered U. And from coding, we know that the mutual information is a lower bound on the size of the code. But the size of the code is in this case the size of the program. And so this gives us a lower bound on the entropy of the program, and therefore also on the size in which the program needs to, of the register which stores the program. So that's roughly the way we proceed for the lower bound. For the upper bound, we just construct an explicit scheme. We just essentially give an explicit method how you prepare this psi and how you run the processor. So it's essentially a constructive tool. And yeah, the surprising thing is that these two quite different things. So the explicit thing, that explicit construction, which gives you the upper bound, and the proof I just showed you, this idea, this information threading idea, leave you with a quite small gap in the case where epsilon is small. I should stress that if epsilon is not small compared to d, so if this doesn't hold, then there is still a considerable gap between the two. So that's also something that is still open. Okay, but I think with that, I'm at the end. So the summary of it is that going from a classical quantum computer, one that takes a classical program as input, to a quantum computer, one that takes a quantum program as input, doesn't lead to much improvement. That's it.
Thank you very much.
Thank you.
One of your expertise pieces in this field.
Yes.
So questions?
I have two questions, if I may. But okay, so one question is about this notion of universal computer. So I was wondering, you know, in the Turing machine, Turing allowed the tape to be infinitely long. So isn't that just because, isn't this somehow a version of what you told us about this? The fact that the universal quantum computer would need infinitely many registers for the data in the program?
Yes, okay, that's a good point. If you compare this whole thing to Turing machines, then maybe one should say two things. So first of all, I assume here that the input in the data is finite. So of course I can now redo the argument for any possible choice of D, and I always get the output. But the idea is kind of, as long as I have finite data, which is already a finite tape. So in other words, would mean as long as the machine should only act on a finite data set, we would want that it also does that after reading a finite portion of the program. I mean, by making things infinite, you just allow, in a way that by waiting longer and longer, you can let it work on longer and longer data sets. So maybe one could rephrase the question I'm asking in this case as saying, let's take maybe universal Turing machine, but let's suppose we are only interested to wait until the point where it computed everything on data up to size D. And then, of course, the expectation would be, this should happen within finite time, even when including the reading of the program and all that. And the no programming theorem, then phrased in this context, tells you as long as you're interested in waiting for a finite time and only working on finite data, you would still not get an arbitrary approximation of what of the desired unitary. But
okay, and now I have a more a question regarding how should I think about your result. This is the transparency I'm looking at. So the cost is proportional to d squared minus 1 over 2. So I think you explained to us that the cost of d squared over 2 essentially is the minimal cost I need to evaluate or to write down one unitary. So now you tell the result seems to be that to compute any unitary with a small error is essentially the same as computing one unitary. So it seems that one pays very little for universality.
Okay. I see. So yeah, maybe that was a bit confusing that in my example I just used one, because when we talk about a universal computer, of course the idea is that the computer should work. I once manufactured a computer and then it should work for any arbitrary unitary. And now if, for example, I would just require it to work for one, then I could build into the computer already the unitary. Or let's suppose I just had a finite set. Let's suppose I would just be interested in 10 different unitaries. Then I would just build them into this machine, and the input would only be a number between 1 and 10. Tell me, now I want to execute that and that unitary. So the idea is
the cost will not be. So I thought that the cost of just inserting one unitary, but which is completely random,
yes,
d square over 2.
Yes, that's right. So at the end, the execution is for one, but the machine is the same for any. So you should think in that way. So first you design the machine before knowing the unitary. So it's like a game. So I give you the machine, let's say, you order the machine, but don't tell me which unitary you want to execute. You may already have one in mind, but you don't tell me. And the game will be, I need to give you that machine, and because I don't know what unitary you have in mind, I need to really prepare build a universal machine. I give you the machine, you then feed in the unitary, the signal unitary interested in, and then the statement is that this machine that I provide to you will have the property that for you to feed in this unitary that you had in mind, you will need that many bits. Now, of course, it could be, you see, the machine, it's the same issue like for coding. If I ask yourself, how many bits do you need to transfer a movie? Then, of course, you're interested in one movie you want maybe to send. And asking how many bits kind of refers to the mechanism. So it could be that by coincidence, the channel that I give you is such that for one particular movie, you need much less bits than for another. So the idea is really that the number of bits is counted by how many different choices would you have and take the logarithm of that essentially. So let's suppose, maybe a better example would be, let's suppose you want to transfer an image which has arbitrary pixels. But if you want to transfer a black image, the agreement would be that you just put in a 0 and nothing else. 0 just means the whole image is black. Then, of course, you could say, oh, for this particular image, the input length is just 0. But this is not the way we count. You would say, no, I have this coding scheme, and because you want in principle to do an arbitrary image, it has to take a much longer input. So you should think of a finite size input. You should think of like there is a number you need to give in, and this number has a certain number of digits. And if this number happens to be a small one, you still count all the digits it could potentially have. You count all the zeros. So.
Thank you.
More questions? I have a question, Renato, regarding this conjecture. Mm-hmm. So in this conjecture, do you assume or think about the set of unitaries as some continuous set in some sort of with parameters?
Yes, that's right. Yes. So that may be, of course, it would be nicer to even have a statement about some discrete set. I wouldn't know how to phrase the conjecture, but that would be maybe another open question. How could we extend the result to non-continuously parameterized sets of unitaries? And I think that would be quite relevant for practice.
Yeah, so, right. That's what I thought, that maybe for practical purposes, you need some sort of discrete set or...
Yes, exactly, yes. Yes.
Okay. Do we have more questions from the audience? Okay, wonderful. Okay, I think this was an extremely clear talk. Thanks.
Thank you. It was a pleasure.
Yeah.
Yeah, indeed, it was very clear. Thank you very much.
Thank you very much.
Thank you as well.
Yeah. And so if there are no more questions, so I hope to see you again soon, virtually or physically.
Yes, let's hope that visits will again be possible. Now I see Tal again, so it's really a long time we haven't seen us. I think it would be great to see you all again.
Yeah, we organize.
Or there.
We organize beautiful weather for you here, but
yes, yes. Actually, I should add, because maybe remember the visit we did with our former president, with Gutzella in Israel. So the current president, Joel Meso, is much more favorable towards quantum things than the previous was. So we have again now a lot of momentum, and I think, in that sense, I think the conditions for, I think at that time there was no, let's say, collaboration or anything on the formal high level that was established. And I think now we are in a much better environment again. We have at least our local ETH government that is behind us, which is good. So,
yeah.
I mean, I just wanted to say that because I remember that we had this visit, and I wasn't particularly happy about the outcome of that at the end on the governance level, so to speak.
great. Let's pursue this point privately.
Yeah.
Yes.
We are
Okay.
I think we are very interested. Great.
Okay, then see you.
Okay, Renato,
you.
see you.
Bye.
Thanks a lot.
Thank you,
Bye.
Renato, and see you.
Bye-bye.
Bye.
Bye-bye.